Thanksgiving break, so that'll come online within the near term. And I hope everyone got my message yesterday that I've just recently turned on the homework thing where it drops your 2 lowest homework scores. I don't do it too early in the semester because it can really make the averages look pretty strange if you've only got 3 assignments but 2 of them are dropped. So I like to wait it till a little bit later in the semester until there's a greater body of numbers that's going into that average. So if you have any questions about your course average, please let me know. I like everyone to feel like they're informed and up to date on how they're doing in the course. These announcements, the inflation homework assignment is due on Thursday, and today we're going to be talking about some ideas in Chapter 15. I hope you're following along in the textbook. It's really an important way to prepare for the final exam that we're going to have. So we're in Chapter 15 talking about cost estimation. And if you think about some of the things we've done so far in the course, you've been analyzing, is option A better or option B? And, in all of the different techniques you've learned, it's always been a given that it's already known how much different projects are going to cost. It's been kind of just assumed or provided directly. So what we're going to talk about today kind of takes you a little bit closer towards the real world where you don't always know with certainty how much things are going to cost. And sometimes you have to make assumptions and do projections in order to prepare cost estimates for the eventual decision making. So that's what we're going to get into now in Chapter 15. So cost estimates are used not only for deciding between options A and B, but sometimes within a given option, you have to decide which features to include. And so you think about the example of buying a vehicle. If you're comparing the possibility of a Honda and a Hyundai, it's just not as simple as which model you're going to choose, but also within that model, there's a variety of different safety and convenience features that you have to analyze whether they're worth it. And so that's true in personal purchases and business purchases as well. So here we're in this engineering building. They had to decide whether or not they wanted to pay extra for the power plugs on the desks. They had to decide whether they wanted a Wi-Fi router in each room or just maybe one in the hallway that was supposed to service all of the classrooms. Actually, that's what they did in the engineering lab building next door. Initially, they didn't have Wi-Fi routers in each of the rooms, and the signal was very spotty. So you have to kind of analyze all of the different possibilities and how cost-effective they are. So here's just an illustration in an airport. If you've got a fixed budget, remember budget limitations guide the decision-making process, can you afford both an automatic external defibrillator? And those are the things where if someone's having a heart attack, you put it on their chest and you kind of stand back and just let the computer shock them and decide if they've got their heart back and that sort of thing. So you see them in airports and malls sometimes. So if you have a budget limit, do you spend your money on a defibrillator or on a wheelchair lift? Because you don't have unlimited funds and sometimes you have to prioritize. So cost estimates can be used to make decisions like that, or they can feed into decisions like that. Now, there's a really important intersection between cost analysis and estimation and engineering ethics. And part of the reason we bring it up now is that people who are involved in purchase decisions sometimes face subtle pressure from equipment suppliers to make decisions on the basis of things other than cost efficiency and the merit of the project that's being, the product that's being marketed. Sometimes a salesman may offer to take someone out to lunch or may bring a gift when they come for an office visit. And of course, anytime somebody does that, then they're kind of implying that you need to reciprocate. And so it's really important to make your decisions just based on the information that's available. And so when you make a cost estimate, the first kind of rule of thumb that's outlined by the book is that it should be sound information that your estimate's based on and gathered over a range of conditions that are representative of the current situation. So for example, if you're trying to estimate the cost of a structure in Alaska, the conditions in Alaska are very different than the conditions in California. And so if your company previously has done a lot of projects in California and you know how much it costs to pour a concrete foundation in California, then it wouldn't be reasonable to try and extrapolate that cost data up to Alaska, because those conditions aren't representative of the current situation. And so there's always going to be situations where maybe the cost data you have is old, and between then and now there's been a lot of inflation. And so those old cost data that you're using kind of to project the new project costs wouldn't be representative of the current situation. So you need to use reasonable data that's reflective of what you're going to experience in the project itself. The second bullet point that the text makes the emphasis of is that you should use accepted methods. So accepted theory and techniques, for example, statistical samples, building budget elements, and drawing conclusions in the way that's kind of accepted in the field. Sometimes it's tough to learn all of those methods, and it's tempting instead just to maybe take averages. You know, an average is really simple. But I'm going to teach you next class period on Thursday a way of doing cost indices that take into account the rate of inflation over time for varying, for different elements of a project. So, for instance, to be more specific, in the economy, inflation is usually between 2 and 3% per year. But different products can inflate at different rates. So the cost of fuel maybe will fall from one year to the next, but the cost of reinforcing steel may go up. And so it would be accepted theory to base your cost estimate on individual price data, but it wouldn't be accepted theory just to use the general rate of inflation for the entire economy for every single item that's going to go into building a structure, for instance. So that's just an illustration of how it's really important to know what are the accepted methods and then to apply them and not just kind of make up your own thing. The third important bullet point here ties into what I was mentioning just before, that you need to keep personal and working relationships separate when you're making cost estimates. And so you shouldn't be related to the person who stands to benefit if you award a contract to one supplier versus another. You shouldn't put yourself in a position where a supplier is sending you on a vacation somewhere. And you know, doctors are often criticized for this, that drug companies will send them down to Florida and they'll go to a convention, you know, and they'll learn, you know, it's going to be continuing education in air quotes, because really what it is just a paid vacation with the expectation that then those doctors are going to prescribe the medication. So, you know, engineering is a regulated profession, and we're supposed to hold ourselves to really high standards, so it's important for us just to make decisions on the basis of what's best for the client, or, you know, what's the most safe alternative, what's the most economical, and not funneling contracts or choosing suppliers on the basis of bias. Any questions about these 3 points? Okay, so cost estimation. One of the projects that I was involved with a couple of years ago, we were doing research at bridges. And what we were doing is we were analyzing the foundation that abutments are built on. And you can see in this picture that there's a little bit of scour, that there's supposed to be rock underneath this concrete face, but over the years, as the water passes through there, especially when there's a really high flow rate, what it does is it undermines that foundation. And so what we had to do is we had to find a supplier that would drill down through the bridge deck, and there's asphalt there, drill down through the concrete, the bridge deck, and then kind of take samples of the rock so we could analyze what's the quality of the rock underneath that foundation. So to do that, the person who was bidding on that job had to put together a cost estimate. And you think about any time work is done in the field, all of the different elements that goes into doing that work. You can see here the orange cones. So they had to factor into their cost estimate the maintenance and protection of traffic. So that means there are people holding either warning signs or stop signs, kind of coordinating the traffic, because you can see they're in the driving lane as they do their work. So that was one element of getting the job done. Another element is just the mobilization of getting people on site. Excuse me. So mobilization is an expense that's usually a specific line item to account for bringing people in from far away. It may Mobilization may cover some of the expenses having to do with their overnight lodging. Another part of the expense was that when they did the drilling and took rock samples, there had to be someone there, a trained geologist or geologist assistant, to log what was coming out of those core samples. And so they had to kind of analyze, take notes, and label what sample came from what depth, how far underground. You can see that these have codes on them. They wrap them up in a paraffin so that the sample doesn't dry out. And then it's stored and transported back to the lab for analysis. And so the time of a trained logger is built into the cost estimate, as well as a per linear foot estimate for the drilling. So every foot that they go down underground, there was a separate cost associated with going that distance underground to kind of account for the cost of maintaining the drill. And so that's just kind of an illustration of a real-world project and all the different components that go into preparing a cost estimate. In contrast, I've had people over to my house to bid on putting in a new driveway. I live on a really steep hill, and the asphalt that I had was crumbling, and it needed to be replaced because I couldn't even get up the hill in wet weather. So it was really striking. Some of the people who came out to bid on putting in a concrete driveway, they just kind of look at it. They'd say, $25,000. They kind of shrug their shoulders and just look at it. The guy that I ended up choosing was the one who got out a tape measure and actually measured how wide is the driveway going to be, how long is the driveway going to be, looked at what's the existing subgrade, is there already a good base of gravel that we're going to be able to use, or does it all have to be removed? Then he's thinking, where am I going to move all this used asphalt? So the removal expenses. The one who was able to actually think through with a little bit more precision on the different components of the project is the one I ended up choosing, because I had the most confidence that actually the estimate was reasonable, and that that person was kind of planning ahead and not just making it all up. So this kind of ties into direct costs versus indirect costs, and we've already discussed this before, but so now that we're in the specific cost estimation chapter, let's go over this again. The direct costs are those that are specifically tied to output or work activity. So remember when we were talking about the Twinkies and a factory that produces Twinkies. So you can say with some detail how much cellophane is required to make a box of Twinkies. The cellophane is the plastic wrapping around the outside. Or you can say how much flour, how much sugar. Those are the inputs that the direct costs are those that are specifically related to the level of output. Whereas that can also include the laborer salaries, because you know how many people you have to have on the assembly line, or the production expenses having to do with the shipping of the item, to get it to market. Indirect costs, by contrast, can't easily be tied to a specific task. And so rather than doing a cost estimate that's on a per item basis, you just usually apply a percentage to indirect costs. Indirect costs come up a lot in the academic world, because when I do research, I have to pay the university a percentage of the budget that comes in. And so I think Marshall's indirect cost rate is around 48%. And so what that means is that if I get $100 to do research, I have to give $48 to Marshall. And what that's covering is electricity. It's covering just being in the building. It's covering their administrative expenses having to do with like the accountants who place all the purchase orders. And so the leftover money, the $52 out of 100 that's left over, is then what I can actually spend on equipment or student salaries and so on. So indirect costs can cover things like the computer systems, accounting, supervisory salaries, building rent, utilities, because you can't directly tie these things, or it's very challenging to directly tie these things to a level of production. So think now back to the example of Twinkies. How many accountants does it take to make a box of Twinkies? Well, who knows? It's not zero. There has to be someone that's taking in the accounts receivable and paying the accounts payable. you have to have some place to do the project, and so there is some cost when you buy a Twinkie. Some fraction of what you paid goes towards the rent on the building where it was made, but it could be a lot of rent, it could be a little bit of rent, you don't exactly know. And so rather than trying to itemize everything, the typical approach is itemize the things that are really obvious, and those are the direct costs. And then rather than itemizing the rest, you just apply a percentage factor for the indirect costs. So that's what we'll do in the coming in-class exercises, is we'll itemize the direct costs and then just kind of lump an additional percentage on top of them to cover the expenses that are associated with indirect costs. Now, when you're trying to figure out how much to sell an item for, there are two different schools of thought. There are two different techniques. And which approach you use for coming up with a selling price partly depends on the type of industry you're in. Whether you're in an industry where everything's kind of interchangeable and you're selling a commodity. For example, if you're selling just raw steel, it's not like you have the ability to charge a lot more for your raw steel than the dozens of other suppliers on the world market. But then if you're selling a specialty item, like let's say for instance that you're Apple and you've got a new iPhone. Well, your iPhone is unique. It's not a commodity. Although there are a lot of other people who make cell phones, kind of the way that Apple has structured their business is that people will essentially pay whatever Apple decides to charge for whatever the latest iPhone is. At least some people will. So let's talk about these two different schools of thought. The first, the bottom-up approach. This is used in the case where competition is not a dominant factor. Sometimes the bottom-up approach is called required price, because the idea is you're just trying to figure out what price is required to cover your costs and provide you with a certain amount of profit that you want to make. In other words, bottom-up approach is it's going to cost whatever it costs because we want to do this certain thing and we don't have a lot of competition. So look at what's built into a bottom-up approach. First of all, you look at the components of doing the thing. And so the components for the direct costs include maintenance operations, the direct labor costs, material costs, equipment and capital recovery. So Apple, which is an example of where competition is not a dominant factor. So Apple looks at, for the iPhone, there's the RAM, there's the processor, there's the screen, there's the glass housing. I don't know, are they back to aluminum or is it still glass? It's hard to keep track. So just like the materials, then they look at the pennies per hour they're paying the people to assemble the item. They're looking at the shipping costs. So all of those direct cost components, they add up the direct costs. And then the indirect costs, they add on top of it. So that's the indirect costs, remember, are like supervisory salaries, the rent, just kind of the things that you can't really itemize as easily. So then you've got some total cost that then on top of that you add an amount of how much profit you want. Now, sometimes you see in the news that when they tear down an iPhone, they can estimate what the actual material cost of an iPhone is. They say, you could go buy this processor for a certain amount. We know how much the RAM is, how much the case would cost. And typically when they do one of those teardowns and itemize it, maybe $600 or $700 on a phone that's selling for $1,000. And so Apple is able just to decide how much profit they want for each of the phones. And then adding all of those different components up, they come up with the required price that they are going to sell the item for, because it covers all of those costs and it covers the amount of profit they choose to earn. So that's the required price approach. The other way, if you are in an industry that has lots of competition, you can't do this, because what you have to do is you have to look at what is the other guy charging. Because if my price is a lot more than his, then my item isn't going to be, it's not going to be sold. So the top-down approach is sometimes called the competitive price. And so rather than building up from all of the component costs and figuring out what it's going to be charged, you say, I'm selling a cell phone, like a middle-of-the-market cell phone, and I think that $400 is what people are willing to spend for that item. So then once you start with what the price is going to be, then you start to allocate where that money's going to go. You say, if it's going to be a $400 phone, I can afford $80 for the processor, $20 for the RAM, $15 for the screen. I'll put $80 into direct labor, maintenance, and operations. So you're kind of like, it's starting with a budget and then deciding a budget number and then deciding where all the amount is going to be distributed. And usually, in the case of competitive price, the allowed profit is very small. You know, the profit margins are thin when there's an efficient marketplace and lots of different suppliers who can produce an interchangeable good. Does everybody understand the difference between bottom up and top down? Okay. Anytime you see a figure like this, your spidey senses should begin to tingle, you know, because I love figures so much and I love making you label curves or draw it again and explain it, stuff like that. So what this is illustrating, look at the axis label. Time spent on an estimate. So this is how long are you going to take to produce a cost estimate? Because if you take just a few minutes preparing a cost estimate for a complicated project, let's say like this building that we're in, if you took 10 minutes to just estimate how much this building would cost to build, then there's going to be a lot of inaccuracy. And so they're saying plus or minus 30%. And that's just kind of a conceptual figure. That's not like exactly 30% accuracy for a 10-minute estimate. Just the trend is that the longer you spend on an estimate, the closer to the true value it's going to be. You know, when you actually build it, then the estimate you prepared at the beginning of the project is going to be more accurate. But then look at the shape of that curve. It begins to flatten out. And you've probably heard the phrase diminishing returns before. Can anybody explain what diminishing returns is? What do you think it means, diminishing returns, when you see this figure? Okay, what do you mean? Okay. Yeah, so, you know, it costs money to prepare an estimate. You know, like for example, an engineer who's working 3 weeks to prepare a cost estimate, that person has to get paid. And, you know, it may be a whole staff of people who are working to prepare a cost estimate. So you have to ask yourself, is the improved accuracy worth the expense of generating that, that accuracy? So what if you had to estimate the amount of money you're going to spend on groceries next week? You could spend 5 minutes preparing that estimate, or you could spend 5 hours. It would be silly to spend 5 hours, you know, calling up every grocery store. How much are lemons? Okay, thank you. You hang up. You call the next grocery store. How much are lemons? Okay, thank you. And you had a list of things, and you're going to find suppliers for each one of them, one at a time. Okay, so you spent 5 hours, and you find the place that sells lemons for 14 cents instead of 18 cents, and you've saved 4 cents by spending all that extra time to gather the data. So diminishing returns means after a while, you're not actually saving that much money by all the additional effort it takes to prepare an estimate. So that's what this is showing, is that the curve flattens. You can spend a lot more time, and there's still going to be some uncertainty in the cost estimate. And so you kind of have to balance the amount of time spent on an estimate and the value of that accuracy. So one should balance the need for accuracy with the cost of obtaining the accuracy. Now, on a building like this, yeah, it probably would make sense to spend 3 weeks preparing a cost estimate, because this building cost $60 million once it was all said and done. But some projects don't justify that importance on accuracy, where, you know, maybe a one-day effort where you've got 15% accuracy is the right amount of accuracy, compared to a week when you spend a week instead of a day, and all it's doing is it's narrowing down the accuracy from 15% plus or minus to 10% plus or minus. So, that's an important cost estimate concept, that there's a trade-off between preparing the cost estimate and the value of accuracy. Okay, so here's another curve, since we're on the subject of analyzing these curves. And the main take-home point of this curve, if you've got it in your notes, what you ought to write is, it's better to make decisions that save money early rather than late, like early in a project. It's easier to save money early on than it is to save money at the end of a project. And so let's look at what these curves are showing, and then we'll talk about how it is that way. The first curve, cumulative committed life cycle cost. So this committed life cycle cost is before the actual cumulative life cycle cost. And committed means you've made a decision. So if you're building a structure, you have to decide, am I going to use concrete, steel, wood, masonry? So you've got all these different options. And once you make a decision, like I'm going to use steel instead of concrete, then you're committed. And you're headed down a certain path for spending. And so what it shows is that during different phases of projects, during the acquisition phase, you're making decisions, and then the amount of money that you're going to spend based on those decisions the slope of this line indicates when you're making a lot of decisions that commit you to a certain expenditure path. So during the needs assessment, for example, when you're just kind of scoping out a project and deciding how big should the building be, you're making decisions on how big the building should be, so the commitment to spend money is before the actual spending of the money. So you look, this lower curve is saying that during the needs assessment, you're not spending a lot of money yet because you're just maybe paying the salary of whoever is doing the needs assessment. But then during the design, during the preliminary design, when you're starting to say there will be 3 floors, and you know the square footage for each floor and how wide the hallways are going to be, you're not actually putting together plans yet, but you're starting to plan out conceptually what the structure will look like. All of a sudden, the committed costs start to accelerate because you've already made the decision on a certain size and a certain layout. And the actual expenditures are still pretty slow. But then once you get into the detailed design, that's where this is having most of the committed costs have already been decided during the detailed design, because there are very few decisions that need to be made during the operation phase. So when the building is actually being constructed, everyone's just executing the plan that had already been decided on. And so, the decision-making costs are flattening out, whereas it's during the design and the construction that the actual life cycle costs are at its steepest. And then during the operation phase and retirement and disposal, that's when the actual life cycle costs start to taper out, because once you have the building and it's already been constructed, then the cost of operating it is just a small fraction of the cost of building it in the first place. We still have in this building to pay the utilities. The building is going to be repainted someday. They'll maybe put in fresh carpet once every decade or so. But there's not a lot of new expenses that are popping up now in the operation phase. And in the retirement and disposal, maybe they implode the structure and haul it away for scrap. There are very few costs relative to the initial construction. So this third figure here, the third curve, potential for life cycle cost savings, what it says is that early in a project you can save a lot of money if you decide on 2 floors instead of 3, for example. If you're doing that scope and you decide to eliminate things that you don't need, that's a huge cost saving. But towards the end of an item's life, there are not very many decisions left to be made. So you can use maybe one person to haul away the rubble or another supplier to haul away the rubble, but probably it's going to be a pretty small margin of savings. And so the potential for savings over the entire life cycle diminishes over time. And that's the important thing to take away from this figure is being able to explain which each of the three curves are, that the committed costs lead the actual costs that are incurred, and that during an item's life, the potential for savings decrease because you've already spent so much. So if we already decided on a 3-story building that's going to have tons of features, and once it's being constructed, there aren't very many decisions that you can make at this point to save money because all of the other, like the sizing and the contents of the building and how it's going to be used, all that's already been figured out. And so it's tough to pinch pennies at the end of a project because so many commitments have already been made. Any questions about these figures? I'd encourage you to review the textbook section that's describing this figure. Cost savings are the easiest to obtain at the beginning of a project before too much capital has been committed to a certain course of action. That's kind of how I distilled it down. Okay, so let's actually learn one of those techniques for cost estimation, and the simplest among them is called the unit method. And the unit method says if you know how much a certain amount of something costs, and you know how much of that item you're going to require, then you find the cost by just multiplying the unit cost by the number of units required. Really simple idea. The complexity arises when you've got lots of different things going into a project. So the unit method says, we know in this building that we're going to need 5,000 gallons of paint for all of the walls and stuff. So you find out how much is the cost per gallon, multiply it by the number of gallons required. And you do the same thing for the carpet. You do the same thing for the steel. You do the same thing for the drywall. All of the components that go into the project, you'd find the component cost per item and multiply it by the number of items. So just for example, these are some typical cost estimates. Operating a car, a commonly accepted amount, 52 cents per mile. That's what I get reimbursed when I drive my car down to South Carolina to work on the FE exam. They say that for 52 cents a mile, that covers the cost of the owning the car, the insurance, the fuel, the maintenance, and so on. I looked up the cost per mile for building a highway. Now, of course, it's going to vary based on where the highway is, but as an average in the United States, $6.2 million per mile of interstate. So that's pretty high. Constructing a house, $225 per square foot. Pouring concrete and so on. So you can do this with just about anything. Find the unit cost of that. So just for some practice, let's use the unit method for part 1 to come up with a cost estimate. And then part 2, we're going to try some decision making with the unit method. So the unit method problems that you're going to see on the homework they're essentially just kind of word problems where you're just applying common sense and a little algebra to figure out the overall cost by looking at all of the things that are going to go into a project. I encourage you to collaborate with your classmates as you're working through this one. It helps to work with another student when you're working on an in-class exercise that has lots of text like these ones do. Okay, so the solution's up on the screen, and this is the unit method because we're looking at all of the units that go into the project and kind of finding the cost for each one of them. So for example, if we know the steel costs, the machinery and tooling costs, the labor, indirect, put it all together, then that would give you an idea of how much to bid on the job. So this is the example of the contractor who comes up and is doing a cost estimate for pouring concrete at your house, who looks at each one of the components of the cost individually. And that's most likely to be an efficient estimate, because the one who doesn't bother to figure out all of the different components, they have to put in a pretty big safety factor there to make sure that it doesn't end up being more expensive than they counted on. So here, if you have a good unit cost estimate, then it'll allow you to bid on a project with confidence that you can cover all of the costs and make a desired amount of profit as well. So anybody else get 566,700? Yeah? All right. Good. Based on how much time we've got left, I want to make sure that we leave enough time for the learning curve that we're going to do. So what I'm going to do is I'm going to put up the solution to this part 2, and I will give you some time to look through it and think it over. But I'm going to start with the solution on the screen so that you can quickly double check your work and not spend too much time stuck, because there's a couple of things here, a couple of angles that maybe if you were to figure it out on your own would take more time than we have available. So I'm going to put the entire solution here from the beginning and give you a few minutes to look it over, think it, copy it down, and so on. And then we'll start talking about the learning curve. Okay, so the setup of this second example is, are you going to make iPhone cases out of cheap plastic or good plastic? And, which one is going to be more cost effective if you're the producer? And so the demand is the same regardless of whether you use the cheap plastic or good plastic. That doesn't vary. We just know we're going to sell 8,333 every month. But what varies is the cost per plastic per pound for the good versus the bad plastic, how many parts per hour can be produced, and so the comparison here is that with the low-grade plastic, what you'll notice is that the labor costs are higher. So comparing the low grade to the high grade, the labor costs are higher for that low-grade plastic. The materials are lower. So the materials are only costing $88 a month for that plastic. But with the higher grade plastic, you're spending $447 a month on the plastic, but then the labor costs are so much lower. And these other costs are lower as well. We said that the other costs are $10 per hour for however many hours per month the production is going on. And with the higher grade plastic, we don't have to work as many hours because there are fewer defects in the parts and the production rate is quicker. So it looks like on a cost basis, the high grade plastic is the way to go because there are savings in other components. And so there's a monthly cost difference, and the second part of the example asks, what's the annual cost difference if you look at this monthly difference between the two and then you multiply it over the 12 months. So you'd actually save $15,000 a year, $15,169.74 if you go for the high-grade plastic rather than the lower quality plastic. So that's just an illustration of how this unit technique can be used for comparing alternatives and making decisions. I wish we had more time for you to go through all those calculations on your own, but at least you got to see what the comparison looks like. And of course, if you want to finish up the calculations, I really encourage that, and you can compare it to this solution by pulling up the video online. But we've reserved a little bit of time that we can now talk about learning curves. And so let's move on to that. This is a picture that was taken in a garment production factory. Sometimes places like these are called sweat houses. It's a pejorative term for a place where the labor conditions are kind of rough and where people aren't being paid very much money. But if you've ever seen a video of a garment factory like this, what's really amazing is how quickly they're able to sew things. Like I saw a video one time of Levi's pants being put together, and they would sew a seam, you know, like a 3-foot seam in just 2 or 3 seconds. Just zip, they just zip through it so quickly and such dexterity, it's amazing. And it's not because they're superhuman, it's because they've done it so many times, they pick up efficiencies along the way. And so anything you do, you probably were able to do it a lot faster the second time compared to the first time. Like think about the first time you changed the oil on your car or swapped out brakes. I mean, it really takes a long time because you're not exactly sure how to get the wheel off. You know, just the things that you learn that first time allows you to be a lot more efficient the second time, and so on and so forth. And so, you know, the same thing is true regardless of whether it's low-end labor that's considered relatively less skilled or high-end labor where it's more skilled. You know, they've picked up hints. You can see they have a really unique kind of chair here that allows them to lay in different positions because you know, how they're accessing the vehicle at different angles affects how quickly they can work. You can see that there's a variety of different tools available. Looks like they've got some battery-powered drills with different attachments on it just so that they don't have to switch out which attachments on the end. They can just grab the drill that they need for the right size. And so as you do things a lot, you pick up the efficiencies, and that learning curve means that it takes less time and less effort to make something the more of the items that's been produced. And so this figure shows that when you are just making the first item, the amount of time taken is relatively high, but then as the number of units made increases, then the amount of time decreases, and it approaches some theoretical minimum amount of time. You know, it's not like the people who are sewing Levi's, if you just give them enough time, then eventually it'll take them 1 microsecond. You know, they can't do that. There are physical limits to how quickly they can work through a problem, but you can make big improvements. And there's a mathematical way of approximating the effect of learning. And it's an important thing for you to be able to factor into your cost estimate because you know, on a job site where a building is being made or in a factory situation where computer chips are being produced, over time people become more efficient. And so the mathematical relationship that allows you to account for that is shown here, this equation on the left. So there's a process that we'll go through. I'll show you an example in just a minute on the whiteboard, and then I'll give you some time to work on the example in the handout. The first step is you have to measure a couple of times to find out the learning curve slope parameter. So for example, you would look at the first one that ever got done, like the first pair of pants, and then the second pair of pants. And that S is the ratio of time it takes to double the number that had been previously made. So when you finished 1 pair of pants, and then you go to 2 pair of pants, you've now doubled your experience when you went from 1 to 2. You've made twice as many at the end of the second pair of pants. And so what you do is you'd find out the time ratio between the two. So doubling would mean going from the second to the 4th, or going from the 3rd pair of pants to the 6th pair of pants. So I think you get the idea of what doubling means, when you double your experience. So you find out that ratio of time, S, and then you put it into this function for n, so it's the log of s divided by the log of 2, and that's what we call the learning curve exponent. And it's an exponent because in the main formula we're going to use it as an exponent factor. Now, u is the output unit number of what you're trying to predict. So if you're trying to predict how long it's going to take for the 10th pair of pants, then you would use 10 for u. And then K is the amount of time or the number of input resource units. It doesn't necessarily have to be time that this is applied to, but it's basically how much was needed to make the first one. And then this equation all the way together will allow you to find out how much time, or whatever the input units are, it takes to make the U item. So if U is 10, then it would be the time needed to make the 10th item. So let me illustrate that for you. Let's say that you're making pants and it took you 85 minutes to sew the first pair, And the second pair of pants was 76.5. The fourth pair of pants was 68.85 minutes. Okay, so the first thing we do is we identify what is K. And K is going to be the number of input units needed to produce the first output unit. So K is 85 in this case, 85 minutes. That's the first pair. And now S, to determine the slope of that learning curve slope parameter, the time for the second relative to the time for the first. So 76.5 minutes was how much it took for the second pair. The first pair, it took 85 minutes. So the ratio here is 0.90. And I could check that because I also know how much it took for the fourth pair of pants. And so let's just check. The fourth pair of pants was 68.85. The second pair of pants was 76.5. And that ratio is also 0.9. So it follows that we're kind of following the same trend of a 90% time requirement each time you double your experience. That's what it means. It means every time you double your experience, you're only taking 90% as much time to make that next unit as you did the one before it. Okay, so now that we have S defined, let's calculate N. So it's the log of S divided by the log of 2. So the log of 0.9 divided by the log of 2. Okay, so that is going to be negative 4.5757 times 10 to the minus second, and then 0.30103. So N is negative 0.1520. And that is the number that I use in this formula anytime I'm trying to find out how much time it's going to take for, let's say, for example, if we're going to do the 10th pair of pants, then what we have is Z sub 10, because we want to find out how much time it takes to make the 10th pair of pants. So then we use K. The first pair of pants was 85 minutes. And then U is going to be 10, because it's the 10th pair of pants, and we take it to the power of negative 0.1520. Okay, so this factor, 10th to the minus 0.1520, becomes 0.70469. So it's going to take 59.9 minutes to make the 10th pair of pants. So we have to check and make sure that it makes sense. You know, it's going to be less time as you gain experience, so it should be less than the lowest that we have here in the problem statement, 68.85. But you can see that the increment of improvement is definitely slowing down. All right. So that's an illustration of how the learning curve is used. So if I wanted to find out the total time required to sew 10 pair of pants, I'd have to do this for the first pair, the second pair, the third pair, and so on. And so it would make sense for us to use Excel if we're going to go through that process. But rather than doing that illustration, I'd like to give you a chance to work here on part 3. So it's on the back side of the in-class exercise paper that you've got. Let's say that you wanted to find out how long it takes you to solve the Rubik's Cube the 100th time you try it. Now, you didn't measure how long it took the first time, so you're going to have to back calculate. Once you calculate S, like you can find S from the second to the fourth, or you can find S from the fourth to the 8th, or from the 3rd to the 6th, you know, whatever. You can calculate S, but then you can use S to estimate how long it took the first time around. Because remember, K is the amount of time it took during the first instance that you did the thing. So here in this problem, it's going to be similar to what I did on the whiteboard. But what you'll need to do is you'll need to, once you determine S, you're going to have to estimate what was the time for the first solving of the Rubik's Cube so that you can define what is K. So the first step is to find S and to check S to make sure that it's a consistent trend, and it is. So then once you have S, then you can find the exponent factor n. And then unique to this example is having to estimate how long the first time was. So altogether then it should be 14.09 minutes to do it on the 100th try. Have any of you ever seen the YouTube video of the guy who's juggling and he's solving it as he's juggling? That one's crazy. I've never solved the Rubik's Cube and I've never juggled. Somehow this kid's doing both, right? And he's doing it in like 2 minutes. So, yeah. All right, well, that's all I have for you today. I'll leave this up for a few minutes in case you need to copy it down.